Okay, hello and welcome back, everybody. So, once again, we have the batch esterification reaction, the one, and in the previous part of this video, we developed the equations, okay? And I just want to point out, it came to my attention that I made a mistake here. Yep, even I make mistakes. It's part of being human. But you know what's the best part? We're not in an exam situation right now. We can correct those mistakes. Yep. That negative sign was not supposed to be there. Why was that not supposed to be there? Let me know in the comments. We're gonna have some discussion going on. So if that negative sign is gonna go away, that means that there's gonna be there's this negative sign is not gonna be there, which means that there's gonna be another negative sign here. Okay, I'm just following algebra, and which means that this negative sign, okay, if you have a negative sign here, then this negative sign would go away. Okay, I'm skipping some algebraic steps. Okay, I'm skipping some algebraic steps, but okay. uh, if you have any doubts, please grab a pencil and paper, please, and try to work out some of the algebra yourself, and I hope it's going to be a good exercise for you guys. So the focus of this video is actually going to be the numerical integration part. Okay, and if you guys followed a previous example, I used trapezoid rule in Excel. Okay, trapezoid rule in Excel. Okay, so I'm gonna be a little old school. You guys are more than welcome to do this using more advanced software like MATLAB, Maple. What else is there? I think MathCAD is one of them. Even Python, NumPy. Damn, the things you can do with Python. Hopefully, I'll make a video on using Python for chemical engineering one day. But damn, you can do a lot of stuff with Python, especially as a chemie. So here I have it. Here I have things set up in Excel, and I have the the integrated form of the equation written here so that I don't make any stupid mistakes. I have my rate constant, my equilibrium constant, my initial concentrations. Okay, so conversions. Let's just make these bold, shall we? All right, we're gonna make these bold and center them. Some nice formatting, nothing fancy. We're obviously gonna start off at 0. And what should be our increments? I'm gonna go in 0.05. That's gonna be my step, and let's go up till 0.4. In this problem, you can't go up till 100% conversion. You can't go till a conversion of 1.0 because you have a reversible reaction. And I'm gonna leave it on you guys as an exercise to find out the equilibrium conversion, and I'm gonna stay below that. So I'm gonna go till, oops, no, not that far. I'm just gonna go till 0.04. Oh, 0.04, yep. That should be good enough. Actually, you know what? We can do better. I'm gonna make the step sizes even smaller because how many cells do I have? I don't have a lot of cells, so I should be fine. So here in my C column, I'm gonna have this entire expression. Okay, the everything that's inside the integral. Let's use some colors for you guys. I'm not getting the options for that. That's weird. Hold up. Oh, there we go. So this entire expression is actually gonna be is actually a function of x. It's an expression of x. I'm not sure if it's a function, but okay, we're gonna roll with it. All right. So let's see. Hopefully, I'm not gonna screw this up. So we have k1. That's gonna be an absolute reference. Okay. K1 and this entire expression, your inlet concentration of A, I absolute reference that. Okay, 1 minus x. I'm gonna try to get through this a little quicker than I usually do. And if you have any questions, just let me know. Now, theta b is just gonna be the initial moles of B divided by initial moles of A, which in this case, it's gonna be just concentrations because we have a liquid phase reaction, right? There we go. There we go. All right, minus the conversion. Conversion is not going to be the absolute reference. Plus CA naught, absolute reference, that again, x squared, oops, my bad, that's not what I was trying to do, my bad. CA naught, absolute reference, times x squared, okay, and divide that by the equilibrium constant, Kc, and that's also going to be an absolute reference. Okay, hopefully my parentheses are closed and taken care of. Let me just check. Give me one moment. All right. Oh, we're good. Thank you. So we're gonna drag this down. Now, again, column C. I'm not sure, like this column does not really have any physical significance. Time, on the other hand, has physical significance for us. Okay, this is going to be the time required to take the desired conversion, and of course at the desired conversion, to achieve a desired conversion of 0, the time is just going to be 0. That's just initializing. And trapezoid rule, please refer to any mathematics textbook, any numerical methods textbook should suffice, and I just do it intuitively. You guys are more than, if following a textbook formula works better for you, then please go with that route. I usually learn to do it intuitively, and if that works for you, then good for you, but if not, then that's okay. So 1/2 times the, okay, hold on, actually this is gonna be my 1.5 times, give me a second. Oh yep, this is actually supposed to be here, and there's supposed to be a trapezoid here. So the area of my column D is actually going to be the area of one trapezoid. Okay, and that's just going to be 0 for the first one. Okay, please refer to a numerical methods textbook to if you have any confusion about the method that I'm using. Okay, 0.5 times the step size multiplied by that. Okay, so for each trapezoid. Okay, so just to give you guys a visual feel without making things too messy, what I'm doing here, let's use this color. Let's say I have a graph that I want to integrate from A to B. Bad boy. Okay, so what I'm doing in column D is just trying to figure out the area of each individual trapezoid. That's what I'm trying to do if I were to explain this visually. So I'm trying to figure out the area of each individual trapezoid in the interval. And the actual time, the value of this integral, the value of this definite integral is just going to be the summation of all of these. So again, initialize equals this plus the previous trapezoid. And hopefully if I do this correctly, yep, that makes sense. All right, this looks good. So I know that in 2.16 seconds, 2.17 seconds, I'm gonna achieve a conversion of 0.4. And now you can play around with a different rate constant. So let's say if I had an even smaller rate constant, obviously it's gonna take me longer. It's gonna take me longer to achieve the desired conversion, right? Okay, now equilibrium. The equilibrium does not affect the kinetics. Keep that in mind. So let's just, I mean, this is good enough. Let's put it back to 0.05 because that's what we started off with. So now let's say I want to insert a graph once again, because that's what engineers do, right? I'm gonna insert a smooth graph, right? So the first thing that I'm gonna do is select my data, get rid of this. I like to start off from scratch, and on the x-axis, actually, hold on, sorry, this should always be out of the way. It should always be out of the way out of the way of the data that you're trying to select, right? Nope. And we're gonna do everything manually because that way you have a smaller chance of screwing up. Okay, so time on the horizontal axis and conversion on the vertical axis. Very good. Very good. And yep, I can make this, I can put the axis titles. Okay, on the vertical axis I have time. Okay, get rid of that. Bye bye, bye bye, bye bye. Time in seconds. Now, okay, the engineering is done. Now we're just playing with the formatting. Okay, and taking a good communications class really helps you, like really helps your career. God damn. So conversion. Okay, I don't need this chart title, right? I don't really like this. Now I can just, like, if I want a different style, okay, I don't know, whatever suits your boat. So essentially now we know, okay, this graph is gonna start it's gonna give a horizontal asymptote. It's gonna give a horizontal asymptote at the equilibrium conversion. Okay, so if you want to do that, you can just drag this down, and drag this down, drag everything down, and let's see what happens. Hopefully this is not gonna be too chaotic. Okay, let's see. Let's reselect our data, and before we select the data, make sure you move it outside. Make sure you move it away from your selected tables. All right, let's select data once again, and this time we're just gonna edit all of that. We're just gonna edit our original series. So instead of 24, it's gonna go all the way till 32. We're gonna go all the way till 32, right? 32. And oops, I did it again. Okay, so once again, the horizontal, we haven't reached the asymptote yet, but now you can just like keep adding points and see where it starts to asymptote, and that's going to be your equilibrium conversion. So yeah guys, that's pretty much it. Thanks for sticking around, I guess. And yeah, just to give you guys a quick recap, as I always do, sorry about that. Okay, batch esterification, we start off with the assumptions. That's a good engineering practice. With the we simplified the mole balance, constant volume assumption. Rate law, it's a reversible reaction. So that's the rate law for a reversible reaction. Very good. We took care of the stoichiometry. Theta is just the initial moles of B divided by initial moles of A. That's the definition of theta. Please refer to Fogler. Okay, then we just combined everything, and once we had our separable ODE, we just performed integration numerically in Excel. And like I said, if you prefer MATLAB, if you prefer Python, if you prefer Maple, then please do whatever suits your boat. I just did Excel because most engineers are going to have access to Excel, but many engineers are not going to have access to MATLAB at their job. So yeah guys, thanks for sticking till the end. Good luck.